Chapter 8, Module 2. In this module, we shall discuss two very important concepts. The first one is triangulation of a topological space, and the second one is the orientation of simplicial complexes. Intuitively, if a topological space can be viewed as a geometric carrier of certain simplicial complex, then that topological space is called triangulable, and that particular simplicial complex is called triangulation of the topological space. Now, we define triangulable topological space formally. Let X be a topological space. It is said to be triangulable if there exists a finite simplicial complex K such that X is homeomorphic to the geometric carrier of K. We usually denote the geometric carrier by mod K. K is called a triangulation of X when X is homeomorphic to the geometric carrier mod K, and mod K is called a polyhedron. Now, let us take an example. Consider X as the collection of points cos theta sin theta, where theta varies from 0 to pi by 2. That means, it is an arc of a circle in R2. We choose 2 points A and B from X with theta equal to 0 and theta equal to pi by 2. That means, A stands for the point 1 0 and B stands for the point 0 1 in the plane. We take the simplicial complex K as the 0 simplex A, 0 simplex B and the 1 simplex AB. We claim that this K is a triangulation of X. How do we get it? Let us define the homeomorphism psi from X to mod K given by the point cos theta sin theta is mapped to the point cos theta by cos theta plus sin theta, comma sin theta by cos theta plus sin theta. In the next example, we take a cylinder. C is the cylinder which contains all the points x, y, z in R3, satisfying the conditions that x square plus y square equal to 1 and z lying between minus a plus a. Then C is homeomorphic to the quotient of a rectangle x y, where x lies between minus 1 plus 1 and y varies between minus a plus a, with the identification that the point minus 1 y is identified with the point 1 y, where y is any point between the closed interval minus a to a. The following diagram gives a triangulation of the cylinder. Here we see that the left edge of the rectangle A0 A1 is identified with the right edge of the rectangle, that is again A0 A1, and this identification gives us the cylinder, and the diagram shows how it can be triangulated. Next example gives a triangulation of a torus. Suppose a torus is given. Torus is nothing but a rectangle with the identification described here as the left edge is identified with the right edge and the top edge is identified with the lower edge. So, we get a torus flattened as a rectangle as shown in the diagram, and we get a triangulation by means of drawing triangles in the surface. Similarly, if we take a Mobius band, then Mobius band is a rectangle identified by the formula -1 y identified with the point 1 minus y, giving a twist, and therefore, the triangulation of the Mobius band is obtainable just as shown in the diagram. Observing the above examples, we may conclude that any triangulation of a compact surface satisfies the following two conditions. The first condition is that each edge is an edge of exactly two triangles, and the second one is that if V is a vertex of a triangulation, then we may arrange the set of all triangles with V as a vertex in cyclic order T0, T1, T2, Tn with Tn equal to T0, such that the consecutive ones Tj and Tj plus 1 have an edge in common for j varying from 0 to n minus 1. In this example, we see that this is not a triangulation of a Mobius band. Why so? If we take the second and third triangle shown in this diagram, then the vertices of the second triangle and the vertices of the third triangle are all same. Thereby, what we get is that three geometrically independent points give rise to two distinct hyperplanes of dimension 2 containing all the 3 points, which is a contradiction. So, this cannot be a triangulation of a Mobius band. Also, we observe that one may have several triangulations for a particular topological space. So, given a topological space X, one may get two simplicial complexes K1 and K2 such that X is homeomorphic to the geometric carrier of K1 and it is homeomorphic to geometric carrier of K2. A very simple such possibility is depicted in the following diagram. Here, both the diagrams give two different triangulations of the same space, that is the projective plane. In a previous module, we have defined simplicial complex and geometric carrier of a simplicial complex. Now, we shall introduce orientation of a simplicial complex. To define orientation, we need to define orientation or direction of a simplex. Now, we begin with certain illustrations which will lead to the definition of orientation of a simplex. We begin with discussing possible definition for orientation that comes naturally in our mind. Suppose sigma 1 is a one simplex with vertices V0 and V1. The geometric carrier of sigma 1 is a line segment between the vertices V0 and V1. Of course, there are two possible directions one may think of. one is V0 to V1 and the other one is V1 to V0. If V0 to V1 is considered as positive, then the other direction, that is V1 to V0, is negative. So, we may write plus sigma 1 for V0 V1 and certainly then minus sigma 1 will stand for V1 V0. So, an oriented one simplex is expressed as V0 to V1 with an arrowhead starting from V0 directing towards V1. In the second illustration, we take a two simplex V0, V1, V2. Then the geometric carrier of sigma 2 is the region on and inside the triangle with vertices V0, V1 and V2. Our intuition suggests that there are two possible orientations. One is anti-clockwise and the other one is clockwise. If we take the anti-clockwise direction as positive, then plus sigma 2 is V0, V1, V2, V1, V2, V0 and V2, V0, V1. Then clearly minus sigma 2 will be V1, V0, V2, V0, V2, V1 and V2, V1, V0. Third illustration is with sigma 3 as V0, V1, V2, V3, the tetrahedron, the three simplex. Now, if we take sigma 3 as V0, V1, V2, V3, then it is difficult to illustrate the possible orientations of sigma 3, because there are more than 2 degrees of freedom exist in rotating the tetrahedron. So, in fact, for any m simplex with m greater than equal to 4, we are unable to visualize the geometry of the simplex sigma m. Hence, we need to formulate something algebraically without involving the geometry of the said simplex. Also, the definition should be a generalization of the aforementioned natural concept of orientation. So, to define orientation, we need to define what is ordering of vertices. Suppose I have m plus 1 many vertices V0, V1, V2, Vm, then we say that V0 is less than V1, less than V2, etc. up to less than Vm if and only if the simplex V0, V1, Vm is a positively oriented simplex. So, if sigma m is an m simplex with ordering of its vertices as V0 less V1 less Vm, then these m plus 1 vertices can be permuted in m plus 1 factorial ways. Among these permutations, half are even and half are odd. If Sm plus 1 denotes the symmetric group on the set 0 to m of m plus 1 symbols, then for any tau belonging to Sm plus 1, the simplex V tau 0, V tau 1 up to V tau m is positively oriented if tau is an even permutation, and V tau 0, V tau 1 up to V tau m is negatively oriented if tau is an odd permutation. So, a finite simplicial complex K is said to be an oriented simplicial complex if each of its simplices are oriented. We now introduce incidence number between two simplexes. Suppose in a simplicial complex K, we have chosen two simplexes, one is sigma q and the other one is sigma q plus 1. That means, two simplexes are taken from K whose dimensions differ by 1. Now, we are going to introduce the incidence number of the pair sigma q and sigma q plus 1, which we shall denote by third bracket sigma q plus 1 sigma q, and we define it by the following numbers. Sigma q plus 1 sigma q, this incidence number will be 0 if sigma q is not a face of sigma q plus 1. Now, if sigma q is the simplex V0 to Vq and we denote plus sigma q by V0 to Vq, and V is the extra vertex of sigma q plus 1 over sigma q, then putting V in front of V0, V1, Vq, if we obtain sigma q plus 1 as positive, then the value of the incidence number is 1, and if putting V in front of V0, V1, Vq, we get negative sigma q plus 1, then the value of the incidence number is minus 1. Now, let us take an example. Suppose K is the closure of a two simplex V0, V1, V2. What do we mean by closure of a simplex? It is a simplicial complex which contains all possible faces of the two simplex V0, V1, V2. If sigma 2 is V0, V1, V2, sigma 1, 1 stands for the one simplex V1, V2, sigma 1, 2 stands for the one simplex V0, V2, and sigma 0 stands for the 0 simplex V0, then sigma 2, sigma 1, 1, this incidence number is 1, sigma 2, sigma 1, 2, this incidence number is minus 1, the incidence number sigma 1, 1, sigma 0 is 0, and sigma 1, 2, sigma 0, this incidence number is minus 1. Now, we prove a theorem which is very important, and we shall see that this result is immensely used in subsequent development of this subject. In an oriented simplicial complex K, if sigma q minus 1 is a q minus 1 face of sigma q plus 1, then summation of the incidence numbers of sigma q plus 1 with sigma q and sigma q with sigma q minus 1, this product is equal to 0, where sigma q is varying over whole of K. Let us sketch a proof of this result. Suppose positively oriented sigma q minus 1 is V0, V1, Vq 1, and A and B are the extra vertices of sigma q plus 1, such that positive oriented sigma q plus 1 is A, B, V0, V1, Vq minus 1. The value of each product term sigma q plus 1 sigma q multiplied with the incidence number sigma q minus 1 is equal to 0 if sigma q is not a face of sigma q plus 1, or sigma q minus 1 is not a face of sigma q. So, the only terms that survive in the above summation are due to those sigma q which are faces of sigma q plus 1 and contain sigma q minus 1 as a face. Therefore, there are only two possibilities for sigma q. One is that sigma q plus 1 which is A V0 V1 Vq minus 1 and the other one is sigma q2 which is B V0 V1 V2 Vq minus 1. So, there are four possible cases. First, sigma q1 is positively oriented, sigma q2 is also positively oriented. In such case, if we calculate the incidence numbers, then we get that sigma q plus 1 sigma q1 is minus 1, sigma q1 sigma q minus 1 that incidence number is 1. On the other hand, sigma q plus 1 sigma q2 that incidence number is 1, whereas the last one sigma q2 sigma q minus 1 is also 1. So, if you take the product and take the summation of all these products, we get the value is equal to 0. The second case is when sigma q1 is positively oriented, sigma q2 is negatively oriented. If we do the same calculation, we will get back the value as 0. If in case 3, sigma q1 is negatively oriented and sigma q2 is positively oriented, then computing the values of the incidence numbers, we can see that the sum of the products will be equal to 0. And similarly, in the last case, when both the simplexes sigma q1 and sigma q2 are negatively oriented, the value will be 0. We shall see subsequently that this result on incidence number plays very important role. Before concluding this module, we point out the aim of this chapter. We shall try to define the simplicial homology groups of a topological space in this chapter. For that, we need to follow a few steps. First of all, we need to define simplicial homology groups of a simplicial complex. Then, if a topological space is triangulable, then we can define the homology group of that topological space by defining the homology groups of the triangulation of that space. Now, there are two questions. First question is, if a space is given, then can we get more than one triangulation? The answer to this question is yes, that we have already seen in this module. So, the question is, if two triangulations of a topological space is given, then can we get two distinct set of homology groups for the given triangulations? The answer is of course no, and since the answer is in negative, we can define homology groups of the topological space X by means of the homology groups of any of its triangulation.